Okay, this is going to be the video for Calculus 3 14.4 tangent planes and linear approximations and differentials. So let me go ahead and share this thing here. And we'll get started. All right, so first of all, tangent plane to a surface. A tangent plane to a surface, if you start with the equation of a plane, which we know is, let me actually expand on this over on the side here. We know that the equation of a plane is ax plus by plus cz equals n dot r0, right? And that produces a constant, right? That constant, we know, I mean, n is a, b, c, right? And r0 is x0, y0, z0. So this dot product is really ax0 plus by0 plus cz0, right? And if you were to bring that back to the other side like this and then distribute combine the a and the b and the c terms, you would get this equation here. So this is the same equation as this. It's just that instead of having a single number out here, that number is separated into its x, y, z components and combined up in this way. So these are sort of equivalent equations. But if I write it in this form, then what you can do is you can divide everything by c and solve it for this term. And if you do that, this is the book's way for defining a tangent equation of a tangent plane to a surface. I'm going to actually show you two ways to do this, the book's way and then another way that's more similar to what we've been doing. But this is the book's way. So they divide everything by c and then solve for z minus z0, you get this. But here's the thing. If we were to stay on the plane y equals y0, then that means this term right here would be 0, and this would drop out. And you would have z minus z0 is just some constant times x minus x0, which is the equation of a line where this is the slope of that line, right? And so if that's the slope of the line, while we're holding y constant on a plane, that means that that slope could also be expressed as the partial derivative of the surface function with respect to x, okay? And then we could use the same thought process and say, okay, what if we stayed on a plane where x was defined to be x equals x0? Then the resulting slope would be fy. And that's where this equation comes from, that if you take z minus z0, where z0 is some point on a surface, and then you set it equal to the partial derivative with respect to x evaluated at that point, times x minus x0, and then you add the partial derivative with respect to y evaluated at x at that point times x or y minus y0. That gives you the equation of the tangent plane to the surface. Okay, so let me kind of show you this visually with an app. I think this is the best way to see what's going on here. Let me change what we're presenting to be something on Chrome here. So this is another one of those online apps. And for this one, you can move a point around here, and basically it shows the tangent plane. So you see how there's a plane here that's tangent to the surface. It's just touching in one spot. And I wish I could rotate this around so you could see it better, but this particular app doesn't have that. The point is, though, that if you pick some point, some x0, y0, z0, like this point here, then you could calculate the derivative in the x direction, right? In other words, if you stayed on a constant y plane and you calculated the derivative in the x direction, it would be this dotted line here, a tangent line. Would be fx, the derivative with respect to x at the point. And then you could find the derivative fy as you changed in the y direction, right? And then those two lines form a plane. That plane is called the tangent plane. And that will vary depending upon where you are on the surface. So if I'm out here, the tangent plane's over here. See, as I move around, the tangent plane is moving around here because the derivatives are changing, right? So yeah, you can really kind of see how it's tangent to the surface if I locate it like that, right? So the tangent plane will move around. That's just a tangent to the surface. And we're coming up with the equation of such a plane. All right, let me go back to the notes here. All right, so for the notes, this is a way to come up with an equation of a tangent plane to a surface. So Let me go ahead and let's take a look at an example of what that would look like. So this is just a kind of a picture from that, right? We have some sort of a surface, right? And then we could find f, if we moved in the x direction, we could find fx, and that would give me the partial derivative in the x direction gives me the tangent at that point of contact as we change in x as the variable. And then we could move in the y direction and have fy, the partial derivative with respect to y, giving the slope of that tangent line, and those two tangent lines form the tangent plane. And this is the equation of that plane. All right, so I think it's easiest to just actually do one. Let's do one. Let's say we have this surface, z equals 2x squared plus y squared, and we want to find the equation of the tangent plane at that point. Okay, so first we would need to find this is the Book's way of doing it, and I'll show you that first. The Book's way is to compute fx, the partial derivative with respect to x, which would be 4x plus nothing, because that's a constant, right? And then you can find fy, which would be the partial derivative with respect to y, which would be 2y. And then evaluate those at the point. So this particular one would be, I'd have to plug a 1 in for x, so it's 4 times 1, so it's 4. So the slope is 4 in that direction. And then the fy would be 2 times the y, which is also 1, which would be 2. And then you can use this memorized equation. You can say, all right, so the equation is z minus z0, and the z0 is 3. So let me write that as a 3. Z minus 3 equals, and then we're going to use the partial derivative in this direction, which is 4, that's the slope, times x minus, that's a 4, x minus x0, and x0 is 1. You know what, let me just start over again. Making a lot of errors there. Z minus 3, the slope in the y direction is the derivative, or x direction is the derivative there, and then x minus whatever the x0 is. And then you could take the derivative here too, and then it's y minus 1, right? So that would give me the equation. If I wanted to, I could solve that by multiplying out, like this z minus 3 equals 4x minus 4. If I wanted it to look more like a traditional equation, z equals 4x plus 2y, and then I've got minus 6, and I take back 3, so I have minus 3. So this is the way the book expresses the answer, right? Or we could rearrange it and say it's 4x plus 2y minus z equals 3 if I move these around. And that looks more like the equations we're used to seeing, okay? That's the book's method. I'm going to show you another method that ties in maybe a little better to the way we've done it. You can use the book's method. It requires kind of memorizing that equation. But you could also do this. You could say, all right, I've got this equation, and let me define an equation fxy that's a function of all of these things, such that we set that that's equal to 0. So if I get everything on the same side, 2x squared plus y squared minus z equals 0, so kind of get everything on one side and call that thing f. Then I can find all three partial derivatives. Fx is 4x, fy is 2y, and fz is negative 1. And then I can say, okay, these derivatives form the direction of the normal vector to the plane by using these. Well, I have to evaluate these at the point. So let me continue here. This would be negative 1. I need to evaluate these then at the point. So if I evaluate this at x equals 1, that's going to be 4. If I evaluate this at y equals 1, that's going to be 2. And if I evaluate this at the point, this is negative 1. And that forms a vector, right? So that vector is 4, 2, negative 1. And that vector ends up being the normal for the plane, okay? So either way, you're going to memorize something, but this is just another way to do it. And then I could have an R0 vector, which is 1, 1, 3 to the point on the surface. And then I can use my standard way of finding planes, which would be, this would be therefore 4x plus 2y minus z equals n dot R0, which would be 4 plus 2 minus 3, which would be 3, and we get the equation 4x plus 2y minus z equals 3, which is the same thing. So whichever method you like, if you want to kind of think of it as of get everything on one side, take all partial derivatives, evaluate them, and those are the x, y, z components of the normal vector, and then combine that with the point in our standard way. Or you can memorize this new little formula for finding a tangent formula where you just calculate the two partial derivatives. Okay, so either way, you can find an equation of that tangent plane to the surface. All right, so the second topic of the three topics in this lesson is linear approximation. Okay, and you can play around with this if you want, but basically I'm kind of showing what comes out here. If I have a surface here, and I have a tangent plane to that surface, at first the surface doesn't appear to be approximating, or the tangent plane is not very close to the surface, right? But if you zoom in on the point of contact, what happens is that this gets kind of to be a gentler and gentler curve until essentially, as you get farther in, the tangent plane does start to closely approximate this over a small region. Maybe only a very small region, but over a very small region, the tangent plane is a decent approximation for the surface itself. Okay, so that's the idea behind linear approximations. And we've seen linear approximations before in regular 2D calculus. If we're not too far away from an x, then the tangent line is a decent approximation to the curve, right? So for the secant line, which is between two distinct points with a fixed delta x, fixed delta y, y minus ya would be the slope of this secant line times the distance in x, right? So you could write that as f of x minus f of a is the change in y, right? So you plug this point a in, you get f of a, plug this x value in, get f of x. F of x minus f of a is the change in y, is going to be equal to the slope of this line, which is delta y over delta x, times the change in x, which is x minus a. And that means that if you wanted to find an f of x point, you could start at some other point that might be easier to evaluate, and then add a little adjustment to that to perturb that slightly to get the value, right? But we said that if we wanted to approximate the surface with the tangent line rather than a secant line, we would take the derivative, and then that same structure would give you that the change in y, which is f of x minus f of some constant a that you choose, is equal to the derivative as the slope times x minus a. Okay, and so therefore f of x can be approximated by taking f at some point a and adding onto it the little change in x times the derivative. Okay, and that's because the f at the tangent is approximately to the f for the secant, right? So this is where we usually first saw a linear approximation formula, that you can approximate an f at x by taking f at a nearby x that's easier to compute, and then figure out the difference times the derivative and add that to perturb that value. Okay, so what we're going to do here in 3D is similar. We're just going to say that we're using a tangent plane to approximate a surface. You don't have to comprehend all this stuff. I just went ahead and copied this out of the book to show the derivation of this, but basically it's the same idea. We're going to say if I want to evaluate a z, a function value f at a value xy, then first I can pick some nearby value, right, where it's easy to evaluate f at xy, like some constant ab. And then I have to add in a little difference caused by the change in the x direction, the change in the x direction. So the change in the x direction times the partial derivative in the x direction. And then I get a little bit of an adjustment here from the change in the y times the slope of the y. So it's just like, you know, this distance here is the slope times the slope of this times this change. So it's like an extra dimensional version of the linear approximations that we saw earlier in calculus. Okay, so let's take an example. Again, I think all these things are easier to see when we do a specific example. So let's say that I have the function, this will do 2D first. Let's say I have the function f of x is the square root of x. But I'd like to get an approximate value for f of 4.2. And I don't have a calculator handy, so I want to kind of approximate it. I don't know that this is going to be that much easier, but this is what's called for. So what I'd first do is I would figure out what the derivative of this is. So if f of x is the square root of x, or x to the 1/2, then the derivative of f of x would be 1/2 x to the negative 1/2, or 1/2 square root of x, right? All right, and then by the approximation formula, if I wanted to know what f of 4.2 is, I could pick some other value which is close to 4.2, but it's easy to take the square root of, like say f of 4. I can take the square root of 4 easily, but then I'm going to have to add on f prime of x evaluated at 4 times how far away I actually am, x minus, and then the difference here, well, actually I need to put the actual x in, so f prime at 4 times 4.2 minus 4. So this is the little change in x. This is the derivative, so this gives me a little adjustment to the y value at the point. And so it's easy to evaluate this. That's just square root of 4, which is 2. And then the derivative we would have to evaluate. Now that's a little harder. If I evaluate this at 4, well, not that bad. It's 1 over 2 times the square root of 4, which would be 2. So 1 over 4, right? So this would be 1/4. The derivative is 1/4 at that value. And then 4.2 minus that is 0.2. So even without a calculator, I might be able to do this. 2 plus 0.2 over 4, right? Which is, what is that? 2, that's 8/4 plus 0.2/4 is going to be 8.2/4. And you could do a little division problem. I still think probably a calculator would be, better, but you get 2.05, and that's our approximate value. Now, if you actually do the square root of 4.2, it's not exactly 2.05, it's 2.049 something, right? So very close. Anyway, this is the idea of approximation. You go a little distance away, like instead of evaluating 4.2, you evaluate 4, and you just evaluate the y value there, but then you have to add on an error, which is this, you're this far different, and then you have to multiply that by the derivative at the easy point to calculate. So for 3D, we're going to do the same thing, except that we're going to have two partial derivatives to add to the point. So if we want to evaluate this function x times e to the xy at the point x is 1.1 and y is negative 0.1, what we can say is, first of all, I can take the derivatives. Well, the first thing I would do is fx. Well, fx here is, actually I'm going to need product rule for this, I believe, right? So it's going to be first times the derivative of the second, which is the copy, times the derivative of the inside, which is y, plus second times derivative of the first, which is just 1. So there's fx. Here's fy. So for y, this is considered a constant. So it's just a constant. And then we have the derivative of e to the yx, which is the copy, but times the derivative of the inside, which would be another x. Right, so I've got, let me simplify this a little bit. We have x times y e to the xy plus e to the xy for the partial derivative with respect to x. And for fy, we have x squared e to the xy. Okay, now we want to evaluate those specifically at the point value. So if I evaluate this at the point 1.1, negative 0.1, and I evaluate this at that point, then the values are fx turns out to be, okay, x is, well, now I'm going to pick a value that's easy, right? So I shouldn't write that. I don't want to use the exact values. I need to use values that are easy to compute, right, but are close to that. So for this value, I'm not going to use 1.1. I'm going to use 1, okay? And for this value, let's go ahead and just use 0. That's pretty close to that. So instead of evaluating at the exact value, we're going to evaluate it at the 0.10. Same thing here. So if I did that, this would be x is 1, y is 0. So I don't need to go any further there. Plus, well, I'll just write it, e to the 1 times 0. Plus e to the 1 times 0. So this is going to be 0 plus e to the 0, which is 1, and so that would be equal to 1. Okay, fx equals 1 at this point that's close to that. Fy would be x, which is 1 squared, e to the 1 times 0. So it's going to be 1 times 1, which is also 1. So fx and fy are both 1. And now I can use this formula. Let me change colors. This formula to evaluate this. So f at 1.1, negative 0.1. Well, first of all, we're going to evaluate the function at our approximate points. So if I plug this should actually read fxy. I'm going to plug 1 in for the x, and then 1 in for the x and 0 for the y. So that would actually also be 1. So this is 1. But then I'm going to take the derivative, 1, fx, times how far away I am in the x direction. So 1.1 minus 1. And then I'll take the partial derivative in the y, which is 1, times how far away I am from the point in the y. So I'm at negative 0.1 minus 0. Okay. All right, so then this would just be 1 plus, when I multiply that in, 1.1 minus 1 plus, that's going to be a negative 0.1 and 0. So these would cancel. We'd end up with 1.1 minus 0.1, which turns out to be 1. So without a calculator, we were able to evaluate this at x is 1.1, negative 0.1. But this is approximate, right? In fact, the actual answer, if you actually plug in, 1.1 here and e to the 1.1 and negative 0.1, the actual answer is 0.98541 something. Okay, so pretty close to 1, but not quite. Anyway, that's how we use derivatives for linear approximation. And the only thing here in Calc 3 is we're saying that we don't just have one derivative times its distance, we have both derivatives times their distances away from the easy point to compute. Okay? All right. Okay, the third and last topic for this video is differentials. And so just definitions of what they are. A differential is a small change, an infinitesimally small change in a direction. So in 2D, right, we said if you have a function curve and you wanted to evaluate it, you could define a couple points on the function like a and x or x plus h, whatever you want to call it. And if you plot 2 points on the line that are separated by a decent physical distance called delta x and delta y, then they form a secant line, and the slope of that is delta y over delta x. So we use these deltas when we're talking about a measurable distance, a substantial distance, okay, between 2 physical points, right? But then we said, okay, if you wanted to bring this secant line, these 2 points closer together, they form the tangent line. That's when the points are almost touching, not quite, but almost touching. And so we have to say there's a very tiny little change in x and a very tiny little change in y. Even smaller than I wrote here, would be infinitesimally small, but it preserves the fact that if the slope is 2, for every 1 unit there, it'd be 2 units there, even though that's a tiny little bit, right? So we switch from deltas to d's, right? dy is an infinitesimally small change in the y direction. Delta y is a physical distance in y. dx, same thing in the x direction. So I just think of them as infinitesimally small changes in distances. And when we take dy over dx, that's the derivative, right? So the same thing is true now in 3D, right? We can say, all right, there's going to be an actual change, right, which we would call delta z, right? If I go a distance x, if I go a distance, actually this would be y, and I go a distance x, then I'm going to get a change in the z that corresponds to that on the surface, right? But what we're saying is on the tangent plane, you have the equivalent of change in the x direction, change in the y direction being defined by the derivatives, fx and fy. And so this change dz is an infinitesimally small version of the delta z change, right? And it's based on infinitesimal changes in x and y. So it's like we're real close to this point down here, making small, tiny little changes. All right, so just like dy dx is the derivative, right? And we could write that as dy is therefore equal to the derivative times dx. You can say that delta z, or dz, is equal to the derivative times the x, but we have to put a term in for the amount of change that came from the x plus the amount of change that came in the z from the y. So this is the differential version of in 3D. And you could write it this way, fx dx, fy dy, or you could write it this way, that this is the partial derivative of z with respect to x, and this is the partial derivative of z with respect to y. What that means is that you have to say, if you have an output and you have 2 possible inputs that are affecting that output, then a change in the output is due to a linear combination of the changes of both the inputs times their derivatives, which basically indicate how sensitive is the output to a change in the input. That's what's going on here. And again, I think the easiest thing to do is to actually do a problem so you can see what we're talking about. And you can see something interesting here too, right? That this dz is composed of two partial dz's, right? Because kind of these are sort of canceling out. So this is a setup for what we're going to cover later in the chain rule, because the chain rule has to be modified to use in 3D. Okay, one more thing before we do an example. Remember back in brief calculus when we talked about the difference between average speed and instantaneous speed? We said that average speed is an actual change in distance over an actual change in time, and therefore we're using algebra when we're finding average. But when we're doing instantaneous speed, it's the limit of that as you allow the differences to get infinitesimally small, so we use a derivative when we need calculus to do instantaneous speed. Similarly, if we use the symbol dz, since that's a differential, then we have to use the derivative, the calculus. So we'll use derivative of in the x direction times the change in x, the differential change in x, and then the partial derivative with respect to y times the differential y. But if we're ever asked to compute a fixed delta z, we just use algebra. And that means we just plug the xy's in for one point and get a z, and we plug the xy's in another point and get a z, and then we just use algebra to subtract the two. So same thing, algebra is used for deltas, right? But derivatives are used for differentials. All right, now I think we can do this last example. Let's say that f of x is a surface is given by, so z, this is z is equal to this f of x is x squared plus 3xy minus y squared. And if y changes from 2 to 2.05, if x changes from 2 to 2.05 and y changes from 3 to 2.95, can we find the differential change dz and the actual change dz? Okay, so let's do the differential part first. This is the calculus one. So we know that this is equal to, I'll use this notation, the partial differential of dz with respect to x times the differential change plus the partial differential with respect to y times the differential change for y. Okay, and so we can say, all right, this dz, well, what's the partial differential with respect to x? Maybe we should just show that as a calculation first. Partial differential of z with respect to x, also known as fx, would be 2x, and then here the derivative would be 1 times the constant 3y, and then that's a constant. And then I could evaluate that at a particular value. So let's evaluate this at the starting point here, 2, 3. So I'm going to evaluate this at the point 2, 3, and get that therefore that would be 2 times 2 plus 3 times 3. So 4 plus 9 is 13, right? Is that right? Is that what I want to be doing? Yeah. And then I could do the same thing for the dz dy, okay, which is also fy. So that's a constant, so it's 0. The derivative there is 1 times 3x, and then minus 2y. And I could evaluate that at this same easy to evaluate point 2, 3. So that would be 3 times 2 minus 2 times 3, which would be 6 minus 6, which would be 0, right? And then I would formulate the formula for it. So let me change colors. dz is equal to this derivative, right? Which would be, let me just write it again so I can write this below it. dz dy, okay? And so this dz dx, we evaluated and found that this was 13. That's the slope in the x direction. So how far have we moved in the x direction? Well, we moved from 2.05. We moved from 2 to 2.05, so that's the difference. And then the slope in the y direction is 0, and the change there is we went to 2.96 starting at 3. So because there's no slope in the y direction, it doesn't matter that I'm moving in the y direction, because that change will produce no change in z. But this z is very sensitive to changes in the x. And that means that if you take 0.05 times 13, you would get that the little change there is 0.65. Okay, so this is how you use calculus to find the differential dz. How much infinitesimal change is there for an infinitesimal change in x and y? When we do this part, we actually use the physical change there. Okay, but if they phrase a question this way, find delta z, then that means to literally find f at the new point, which is 2.05 comma 2.96, and subtract f at the starting point, which would be 2, 3. So we would just not use calculus at all, no derivatives. We would just plug 2.05, 2.96 in this function. So if you do that, I'll just show it being done here. 2.05, 2.96 means we're plugging the 2.05 in for the x, right? And we're plugging the 2.96 in for the y minus the 2.96 squared. So you can compute that, and what you get is delta z is the point there turns out to be, oh, don't I have it figured out? Let's do it. 2.05 squared, I thought I had this in my prepared notes, plus 3 times 2.05 times 2.96 minus the 2.96 number squared turns out to be 13.6449. Okay, and then if we evaluate this with 2 and 3 plugged in here, so that's going to give me, let's see, for x, 2 cubed plus 3 times 2 times 3 minus 3 cubed is going to be, oh, that's not right. Something's wrong here. I'm going to have to do this again. Let me just do this more carefully. So I don't want to show a change here. So f at 2.05 for x and 2.95 for y would be 2.05 squared plus 3 times 2.05 times the y, which is 2.96, minus the y, which is 2.96 squared. So let me just evaluate that again. 2.05 squared, okay, plus 3 times 2.05 times 2.96, but minus 2.96 squared. Sure enough, that's 13.6449. I must have made a mistake here then. F of 2, 3 is, let's see, we've got the x squared, so 2 squared, not cubed, plus 3 times 2 times 3, right? Minus 3 squared. So that'd be 2 squared plus 3 times 2 times 3 minus 3 squared. Okay, hold on here. I think I'm losing my mind here. Plus 3 times 2 times 3 minus 3 squared. Okay, yeah. And that turns out to be 13. So when you take 13.6449 and you subtract off 13, the difference is 0.6449. There we go. So that's the delta z. So delta z is done with algebra only, or pre-calculus. But the differential is done by the derivatives. You have to take every actual change in the x and y direction, but multiply by its sensitivity with the partial derivatives. All right. So that's it for the 14.4 lesson, and go ahead and you can try the homework problems then.